for organizing this workshop and for inviting me. It's really been a great pleasure to be here, and I look forward to 2 more weeks. So I'm going to be talking about auxiliary field quantum Monte Carlo in the context of condensed matter and some quantum chemistry applications. So we carry out simulations for non-relativistic Hamiltonians dealing with the sign problem by putting a constraint. And most of the applications have been done at ground state. And here we could do both realistic Hamiltonians, meaning materials specific Hamiltonians, many-body simulations, and for models. And in fact, one of the recent efforts is to be able to go systematically between the two by dialing parameters and creating model Hamiltonians that simplify the problem. So this, we've had many applications. I think it's been shown to be a systematic approach to go beyond the standard model in condensed matter, which is density functional theory for correlated systems. I'm going to talk a little bit about how we do this constraint and how we understand the sign problem and then control it with approximation using the finite temperature framework. As I said, most of the applications are at ground state, but the hope is this will maybe facilitate the discussions we were beginning to have last week about possible connections with lattice QCD and so on. And then I'll tell you a little bit about recent efforts, talking about first one, releasing the constraint. This is a stable, regular scaling method. And then when you release the constraint, you bring back the sign problem, but it allows you to have an internal indication for errors, and so I'll elaborate on that. And we've also been working on doing excited states, and then this mapping between models and realistic Hamiltonians. I don't have a fixed goal, and depending on how this goes, I could stop before we hit the end. So the work I'll be talking about is mostly done by Werwan Powanto and Fengjie Ma. This is for the electronic materials simulations. These are 2 postdocs. And for lattice models, I'll talk a little bit about Cha-Chen Chen is a former postdoc who's at UC Davis now, and Hao Shi is a graduate student. So the electronic problem, this is really going to be really elementary, but just to set up the notation, we have a simple theory, non-relativistic Schrödinger equation, H psi equals E psi for ground state, and we want to solve this. And where the Hamiltonian takes a form of a 1-body term and a 2-body term, and this is a cartoon of a system we want to look at, for example, transition metal manganese and then oxygen, and you can think of this as being tiled in different patterns to form different crystalline orders. And the black dots are electrons, and some of those could be frozen with the cores, right? And these are the interesting electrons. So the blue terms describe their kinetic energy, the black dots kinetic energy, and the external potential felt by each electron due to these ions. So if it's a naked ion, it would just be Z over R, but typically you take out the core electrons. You combine the core electrons with the core to simplify the problem. So whatever that does, it will create a non-local potential. That's all in here in the external potential, and the lattice structure would also be reflected in there. And then there's an interaction term between the electrons, and this would, given modulation of periodicity, is just 1 over R, right? Repulsion. So the problem is hard because this is not separable. That's one way of looking at it. By that, I just mean it couldn't be written like these 2 blue terms, right? If you could write this as a sum over I, then we'd be all set. But we couldn't do that, so it's a full many-body problem. One of the major successes in physics is to, by brute force, turn it into a blue term. We take this red, and we're going to just write it as a V mean field. So density functional theory, you could view in that framework with possibly some objections, but really it is in that framework of an independent electron. So this is it takes a local density type of approximation, and it has many different acronyms for different forms of approximation: local density approximation, generalized gradient, and so on. There are many. how is it an independent electron framework? Well, it just takes this interaction. It says we're going to make it a functional of local density. So think of this as you're interested in Ri, the ith electron, and this is the density in a little neighborhood near it. I think I have a picture here. And then you map this to a functional that you're going to look up. And this functional, as has been mentioned several times, came from David's pioneering calculations with the electron gas. So you look up this table, you say, if I have this density in that little area that I'm interested in, here's what the exchange correlation effect ought to be. And that's a function of the density and the coordinate, and then this is blue. In second quantization, the Hamiltonian, the blue terms, all of these are lumped into, you choose some basis, and it could be plane waves, grids, or in chemistry, use Gaussian functions that are locked to atoms. So once you choose those basis functions, this term gives you two operators, one creation, one destruction. It's a one-body term, and these matrix elements are known. They're dependent on the basis you choose. And then this is the two-body form. It has four of these operators, right? It's two-body. And LDA in that language just says H2, you bite force, write it as a functional of the density, and then the density operator. Think of I now as labeling a grid in real space. So you put things on a grid, and I is a label of the grid. So at a particular grid point, the density operator times that density functional that's dependent on the local density. Hartree-Fock would just be taking two of these and make a bracket. This bracket means calculate an average with respect to your current state. And then these are the operators, so it turns into a blue term, just one operator. And in practice, this is done by assuming some solution and then just self-consistently calculate this, solve for a new solution, and until you reach convergence. So this framework has been tremendously successful. As I said, it's really the bread and butter. It's the workhorse in condensed matter, but it's often incorrect in strongly correlated systems. In high temperature superconductors, it gets essentially most of the physics wrong. In magnetic systems, low dimensional systems, so on. For example, nickel oxide is an insulator, but if you carry out these calculations, most of them just tell you it's a metal. Even in conventional systems where DFT has had a lot of success, small errors can make qualitative sometimes differences if you want to really be able to carry out predictive calculations. And that's the goal here, is to be able to make predictions of materials' specific properties. So here's an example of the second category where this is a typical structure in condensed matter with transition metal in the middle, and these are the B atoms, oxygens. The B atoms are here, the bismuth atoms. So this is scandium bismuth O3. And this is supposed to be a ferroelectric material. What happens is when you squeeze this crystal, it breaks symmetry. This center thing would move one way or the other, sometimes diagonally. And that generates a current. So you squeeze, there's a mechanical response of a current to it. And vice versa. If you run a current through, it'll give you a mechanical response. And you have a piece of this in your cell phone. And the Navy has been very interested in this for underground communication. So what you would like to do is to design materials that have a larger response. If you do density functional theory on this material, it's hugely successful, predicts things very well. For example, you set up these ions at fixed locations, and then you calculate the energy equation of state, and then you minimize it, and that tells you, for example, what the lattice constant is if you fix the structure. Otherwise, it can help you optimize the structure as well. But when you calculate the lattice constant, it's very successful. It's within 1% of the experimental value. But that 1%, if you go off 1%, it wipes out the entire effect. There is no ferroelectricity. So there's been a lot of calculations, but how that's done is you sit this at the experimental lattice constant. Then you do see this effect. But that's, according to the theory, is not the ground state. So I'll give you another example, and this is, has come up quite a few times, the Hubbard model. I want to tell you one result, but mainly just want to use it to set up some notation when we talk about methods. So this is the simplest model, which kind of exemplifies many of the issues in condensed matter. What are the key issues in condensed matter? We're interested in the interplay between correlation, or particle interaction, and the environment. The environment includes, for example, these lattice structures, and David mentioned last week disorder. That's another big, interesting element in condensed matter that creates a lot of phenomena. So these three things, or two things, environment, including both of those. The Hubbard model right now, as I've written it down, doesn't have that, but you can imagine by putting site disorder to mimic a material. So what is it? It has a square lattice, or cubic. The square lattice has drawn a lot of attention. And you have electrons of two kinds, spin up and spin down, blue and red. They hop from a site to a near neighbor site, and that's this kinetic energy term. And then when two of them are on the same site, blue and red, they pick up an on-site repulsion to mimic the Coulomb repulsion. And this was proposed a long time ago as a model for d electrons in transition metals, where there's a strong local interaction and then hopping. So the half-filled case, which was also mentioned last week, corresponds to, on the average, 1 electron per lattice site. And this is a limit that corresponds to the case of mu equals 0 that was mentioned in the last QCD calculation. There's no sign problem. There's a particle-hole symmetry. And this is well understood, that the ground state is going to be antiferromagnetic with a preference for one kind of electron to be on one sublattice and the other one on the other one. So there's antiferromagnetism. And this is essentially repeating the same thing. It's the 2D system has drawn a lot of interest because sort of as a model for the copper CuO2 plane in cuprates, these high temperature superconductors. At half filling, I mentioned its antiferromagnetic order, and this is a schematic representation of a spin-spin correlation. If you calculate the ground state spin-spin correlation by sitting at one particular lattice site and asking, what is the spin? If I have an upspin, what's the correlation? Then this is the pattern.
What happens if the lattice is triangular?
There's frustration. Actually, good question. There's not a whole lot known about the triangular lattice. So this is because it's bipartite, and at ground state, what's shown here is the spin-spin correlation. And as you go from here as a function of distance, you can see you're going to just pick up the two near neighbor, and that's negative, and then you pick up the positive ones, and so on. It just goes up and down. It's an antiferromagnetic order. One thing I want to point your attention to is I've drawn two misleading pictures here, indicating as if these are like Wigner crystals. The up electrons would localize on one side, the down would localize on the other. That's very wrong. Its 0.2 is the correlation. So it's very wavy. It's very quantum mechanical. 1 would be the Wigner, the full crystal limit. But this is far from that at interesting interactions. It's a very wavy-like thing, but it has long-range order. One way to denote this is to think of the, if you draw a diagonal, right, these are all up spins or down spins. So I'm going to use pictures like this. If you see a picture like this, it just shows that it's antiferromagnetic the whole way.
What would happen if you increase U?
Um,
you still have,
yes.
You don't go to the
so
limit?
what you're going to see as you increase U is from small u, this amplitude is smaller. You increase U, it just keeps getting bigger.
So
right, you get a stronger limit. But the approach to that is very, very slow. Good. So one question is, what happens to the antiferromagnetic order upon doping? What does it mean, doping? Well, you just take away some electrons, and that's the actual cuprate high-temperature superconductor. The reason this is thought of, you might wonder, we do too all the time, why such a simple model would have anything to do with these high-temperature materials. That's still not known, but it's strongly believed that this contains a lot of the key. And really, the motivation, as far as we can see, is just two. One says the copper-oxygen 2 plane is a key, and that's mimicked by a square lattice. And two, superconductivity appears to arise out of doping of a Mott insulator. Well, this is a Mott insulator, and when you dope it, what happens? So one of the big questions, aside from electron pairing, which is the key, is what happens to this magnetism? So that's the question. You know, when you take away some, there's free space. In some ways, the kinetic energy would want to distort this order and put things to occupy that space. And on the other hand, this serves to minimize the potential energy. Right? So what happens? There are many answers to this. This is from a textbook, standard textbook in condensed matter. And it draws 6 phase diagrams, 6 possible candidate phase diagrams for the Hubbard model. This is Oral's question, U over T on the vertical axis. And this delta is doping, which I'm going to call H. So 0 is half fitting, and go to 1, it's an empty lattice. Right? So this is, so cold atoms would be like here on the right. So you can see they're very different. Right? You can't read the details, but the predictions are drastically different. There are many answers. This is the second edition, which showed up 3 years ago. And these basically are the same. The bottom panel is replaced now by 2. And the conclusion is, you can see the phase diagram have started to converge. Saying converge because you see this is metal and that's insulator, and this has changed a little bit. Right? The critical U has changed some, so it appears to have converged. On this axis is where we know the answer, except if you look at this a little bit more carefully, this is incorrect, because we just showed a diagram, right, from quantum Monte Carlo that says this is all the way insulating, right, and this is predicting a metal.
So on the horizontal axis you have
this is doping, right. So why is this hard? It's just because there are many, many states, competing states, that are separated by tiny energy differences. Right? So numerically, most of these are in fact, you know, approximate Hartree-Fock or somewhat beyond Hartree-Fock type of approaches. And this particular, the latest, is from what's known as a dynamical mean field theory, which has seen a lot of success in treating strongly correlated systems. And this is really an assumption within DMFT. Right? It's not really the correct answer.
Can I ask you?
Yeah, so optical lattice now is supposed to be able to mimic this model. That's why there is a lot of excitement and revived interest in trying to understand this and hopefully be able to make some predictions for these experiments. But you know, if the experiments can get to low enough temperature, hopefully we'll have some answers. Yeah.
I'm asking simply because I don't know. You see, you showed a relatively modest U,
Mm-hmm.
T4 or something.
Mm-hmm.
The Smith-Spin correlation function.
Mm-hmm.
And it looks very far from the Wigner crystal. So that means quantum fluctuations are pretty big. So you'll have occupation probability per site which fluctuates around 1. It's not 1. So why that doesn't allow current to flow?
Why doesn't it? Well, we don't. So
because you said you see that's the average picture, but you have fluctuations. And
right.
I would think that probably
good. Well, there is long-range order. That's the key. So there is quantum fluctuations. There is a lot of exchange, local exchange, but there is also long-range order. So if you calculate a current.
So you'll find the same thing.
No, if you have a liquid, it would be a super, because it would be a liquid. It would be like a super solid or something. It would maintain both crystalline order, and it would be mobile.
So you mean if I apply an electric field to the Hubbard model, the current won't flow?
At half fitting, the current will not flow. Yeah.
So if I calculate the linear response,
Yes, it'll tell you that it's an insulator.
One way to think about it is you get these huge fluctuations, so you have a lot of unoccupied sites or doubly occupied sites. But those holes in doublons are bound together. They can only go a few lattice sites away before they have to come back together, like quarks, right? They're confined.
Mm-hmm. Okay, thank you.
Good.
And then you have a phase transition where all of a sudden they become unbound, and then you have a metal.
Okay.
So coming back to density functional theory, the independent electron solution, right? This is, I'm just reminding everybody the notation again. We can always solve a one-body problem, and whatever basis you choose, right? You find some single particle energy levels, and here's this manganese oxide again. I'm trying to draw 2 orbitals. These are just single particle wave functions written in that basis. So these are that's a ground state. and that's a first excited state. This is the single particle state. And then if you have electrons, you just occupy them. So if you have two upspin electrons, you just occupy them. This is the ground state picture. And then if you have two down electrons, you occupy them, and that's the Fermi level. So the solution to this problem would look like this, where psi 1, psi 2, these are just coefficients. Given that basis function, these are coefficients in front of the basis functions to represent a wave function. So this red object is one wave function, and the green object is another wave function. And if you have more, you just pile up more columns, right? So that's a way to think about a Slater, what I'm going to refer to as a Slater determinant. This means if you observe second quantization and you do algebra on it, all the fermion symmetry would be properly maintained. So coming back to this earlier comment, Hartree-Fock, we do this, right? We take a bracket. So that just means the bracket with respect to that object that I just showed you, right? You make a wave function, and then you calculate this expectation, and now you get this one-body operator. The whole Hamiltonian is one body, and you solve it again. So basically, the independent electron framework says you change the Hamiltonian, and then you demand a single determinant solution, right? That's the approach. Now we ask a question. Can we turn the Hamiltonian blue without changing it, right? All of this changes it. Density functional theory claims that there is one limit where you don't have to exactly change the Hamiltonian, although the wave function would not be a wave function. But can we make it more rigorous? Can we change this to blue without changing the Hamiltonian? The answer is somewhat surprisingly, it's a words game, but yes. If you consider this propagator, e to the minus tau h, where tau is going to be, we're going to make it small, a time step, then you could write e to the minus tau h in this form, tau h1 and h2 with higher order terms. In practice, we're going to make this more symmetrized to go to higher order. But for the thought experiment, just think of tau as going to 0. So if you consider this propagator written here, then the independent electron propagator, HLDA, as we said before, we just replace this red by a blue, which is the exchange correlation functional that contains the parametrized answer as a function of density. Then one way to do an LDA calculation, local density or mean field calculation, is to say, okay, you could take a single determinant wave function, take a guess, solve the Hartree problem or whatever, write down some arbitrary orbitals, and then just take this e to the minus tau LDA and hit it once. And what happens, this will lead to a new determinant. And the reason is because this is one body, and this is Thouless has a local connection. Thouless theorem says if you have an e to the tau one-body operator operating on a determinant, it leads to a new determinant. So that leads to a new determinant. You could do this again. Now take the Hamiltonian, which is dependent on the current state, right? This bracket that we do. Calculate this again. Now it's n1, right, from that, and then just hit it again. And you keep going. And by the time you're done, what do you get? Well, you get the ground state one particle solution back, right? So this is one way to carry out a local density calculation. In practice, people don't do that. They do steepest descent or something. But this is perfectly good. In fact, time-dependent Hartree-Fock or time-dependent DFT, you could think of this in this language. Okay, so as advertised, this leads to a single determinant solution, right, because it's independent electron. Now let's think about the many-body case, the question we just asked. If we have an H2, can we write it into blue term? Well, the answer is yes, sort of. You can write it as a blue term squared. And that's not too difficult to see. There are 4 C's. You can factorize them to write as 2 C's squared. And so that's this object, sum of 2 body operators squared. Gamma is an index that labels them. It takes sometimes a lot of terms to realize this. But whatever combination of this 2 body, you can always do that. And
attractive the way
no, anything.
you put the minus sign.
V I'm going to allow to become complex. Right? So anything goes. So then you apply, so this is, all of you will realize this, recognize this by now. This is the Hubbard-Stoyanovich transformation. You can now write, because you want e to the minus tau h2, right? You can write e to the v squared. Notice I left this minus sign here. So it's e to the v squared. And that's this, you complete a Gaussian integral, and you can get this back. So this is fluctuating field, that's in purple, sigma, and then a one-body operator. In other words, to summarize, we've taken e to the minus tau h, we've written it as e to the minus tau h1, which is a blue term, and then an integral that corresponds to this, and then some fluctuating fields, and then a one-body operator. So we can't write it as a single one-body operator, but we can write it as a sum over a lot of one-body operators that live in external fields. And that's the idea of the Hubbard-Stratonovich transformation. So then if you go back to here, you repeat the same thing, what would happen? Well, you would start from a single determinant, and because this is an integral, you're supposed to integrate over many fields. That would lead to many determinants, and as you go on, the number of determinants would grow exponentially. But if you were able to keep track of that, you would get the ground state exactly. Okay? Now we're going to use Monte Carlo to sample that, and that's auxiliary field. So a comment here, there are very many different forms of this to do this. Hartree-Fock, pairing different ways. We're just going to use a generic form, but they can affect your accuracy and efficiency and so on. So you also, I'm going to present you the unimportant. We're not going to worry about the technical details. Of course, you have to do important sampling to make this scheme practical. So going back to the Hubbard model, this is u over t of 8, which is equal to the bandwidth. This is the worst region of parameter. This is where you want to be. Supposedly, high TC happens here at density of 0.9 or so. And this is only a 4x4 lattice. And if you do this calculation that I just outlined. Now, note, you might be worried about this one thing that we said we start from a single determinant. We're going to do this integral. We're going to get many determinants. And then each one of them would become many determinants. Again, it's an exponential growth. We don't do that, right? We start with a population of walkers. If you want, just make them identical, all Hartree-Fock solution. Each one of them would Monte Carlo sample another determinant or two. And each one of them would sample one or two. Because if you converge to the ground state, right, the time average and ensemble average, those are the same thing. So the population doesn't explode. It stays a constant. And when you do this as a function of imaginary time, you can see that it starts out, the energy, this is high, and then eventually it seems to converge, and then it fluctuates more.
What you're saying is that instead of generating many determinants, you sample many determinants.
That's right. That's right. Instead of following the recipe to rigorously generate all those determinants, we sample. By the way, for the Hubbard model,
is rigorous too.
Explicitly, you're right. Instead of explicitly.
Stupidly.
Okay. So in the Hubbard model, e to the minus tau u, this is the on-site interaction, right? This is one example of how we execute this BX, this integration over one body. Each site has an on-site repulsion, and it turns into an Ising field that lives on the site. The field could be up or down, and then this is e to the some constant that depends on u and tau and so on, and then n up minus n down. So it's decoupled the two operators into one-body operators.
So the determinants that you get may be positive or negative.
That's right.
So how do you sample?
Hang on just one second. So this is brute force. So you just respect the sign. If it says it's positive, it's positive. If it says it's negative, you keep track. Okay? And this has exponential noise because of this fact that some of them will be positive, some of them will be negative. So this is most severe at lower T. Lower T here just means I'm now sneaking in the finite temperature formalism. But the ground state, it just means projecting longer, making the path longer, right? The problem gets worse at lower T for larger system sizes, or in the most correlated regime, like here, it's worse. If you have, instead of a density of 0.875, if you have 0.5, it would be much better. The error bar would be much smaller. So this is the sign problem, first appearance here in the talk, but it's been noted for a long time. Now I'm going to take a small detour. In order to explain how we're going to deal with the plus minus, I'm going to introduce the finite-T method, which is really just the same thing, but trying to make a connection with the lattice approach. So standard finite-T method is due to Blank-Beckler, Scalapino, and Sugar 30 years ago. The partition function in the finite temperature case you want is beta 1 over kt, right? And then you want to evaluate a trace of e to the minus beta h. The one difference is here it's going to be in grand canonical ensemble. And with the Trotter breakup that we introduced, you're going to write this as e to the minus tau h many times, and the number of slices is beta over tau. We write it formally like that. And then what you need for an observable is this trace ratio, which now remember this little formula here, e to the minus tau h. I've written it slightly differently. We had, this B has the propagator of a single particle form. It's a function of a field, external field. And this external field is a vector. Like on the Hubbard model, it would be one Ising field every site. And I've written it as an explicit sum, but it can be an integral. Doesn't matter. You have to integrate over all the auxiliary field possibilities. So e to the minus tau h can be rigorously written as this. Sum over a one-body operator. The one-body operator depends on the field, and you integrate over all field values. When you plug this in, right, you get in the trace, I'm just writing this out foolishly, every time slice. So there are L time slices, and you get L different fields, and here too, right? This is just like the lattice approach. And you can integrate out the fermions. You analytically evaluate the trace over fermions and particle numbers. And this trace turns out to be a determinant of one unit matrix plus these B's. Now, I've gone back and forth. Slight change of concept. This B is meant to be a propagator, e to the minus tau, an operator. This B is that operator, but represented in some finite basis in matrix form. Okay? So this is the matrix product, and the unit matrix, and then you take a determinant. You sum over all the fields. So the fermion degrees of freedom are gone, but instead you're supposed to sample over this path, finite length path, of auxiliary fields and evaluate this determinant. And so that's how you sample the fields by metropolis, for example. You wiggle, you carry out a set of paths. You start them by some value, and then you wiggle them around according to metropolis, accept and reject, until you reach equilibrium, and then you just calculate the expectations. So as t lowers, the average sign of this determinant goes to 0 exponentially. This is, we've commented on this before, and we need to control the sign problem. So, oh, sorry, I meant to, okay, that's the Hubbard-Stronach form. So the sign, what does that mean? You could write this, this is the trace, this is the denominator, as a sum over these fields, and then the dx, and this, I think Filippi wrote out the same formula, and then the sign of this determinant. And then this is the absolute value and sign and observable. This observable is easily computed for any path. Now, this is at now temperature, so low temperature is that way. For that lattice that we just showed, the 4x4 lattice at 0.87 density. And you can see that this average sign starts out at high temperature being very good, 1, and then it drops exponentially to 0. Right? David?
One question is, in the original form there, where your equation is, where you have the product of B's, you have something that's local in time. Because when you do the trace, it's no longer local in time, right? So if you change any Ising field, you have to recalculate the whole product.
That's right. So if you change any field here in the path integral, the whole determinant changes. But it's like in the Metropolis update, if you modify one field, there are tricks to calculate the ratio of the two determinants.
By doing the trace, you gain in the sign?
You gain in the sign, and you don't have to explicitly, this is grand canonical ensemble, so it includes, having on the average 1 particle, 2 and 3, and so on. You don't have to worry about that anymore. But the price you pay is that these B's are full. In other words, you're treating the full set of single particle eigenstates.
Oh, so it's not a sparse matrix?
It's not a sparse, it's sparse, but it's big. It's still sparse in that, the operator, in the Hubbard model, it's sparse, because the kinetic energy is sparse in momentum space, and the Hubbard-Stronach field is sparse in real space. So it's still sparse. So I'm going to now take this apart again to introduce this idea of how the sign comes about and how to control it. So this looks long, but it's actually, if bear with me, we can just walk through it. This is the partition function again. It's trace. You want to do this. And we already did this to arrive at here, right? To integrate out the fermion trace to arrive at here. But I'm going to go back and do a strange thought experiment of going step by step. So we're going to take this first e to the minus tau h. Doesn't matter which one you take. This is rotationally invariant in time, right? So take the first one and write this. Remember that we have e to the minus tau h is sum over x and then bx. Wait, I should have it somewhere. So replace that by sum over x bx. So then it just, you pretend the rest of them, you don't, you freeze. And then I'm going to define this sum integrand here as, call it P1 x1. It's only a function of one set of auxiliary field, the time slice at 1. And then I unroll a next one, bx2, and that now it's the path integral is over x1 and x2. And then I'm going to call this integrand P2 x1 x2, which is a function of 2. No. This is formal. It's exact. I'm just.
No, if you sum all of them.
Yes, if you sum over all the x's, it's exact, right? So, but I just want to carry out a thought experiment of how we arrive at this, and that's going to prove useful. Okay. So right now it's just it's busy work, right? It just rewrote the whole thing, and then when you unroll everybody, you get back the original thing, and then you have to sum over all the path.
So you're simply proving that these determinant.
No. Just bear with me. I'm just going to set up a way to think about it, right? Which is not a particularly smart-looking way, but it's going to expose the sign problem. This sequence of numbers, right? These are growing. These are integrands whose size, whose space grows, right? They contain more and more fields. So now I'm going to carry out this experiment by pretending that every time when I unroll one slice, the rest of them are known exactly. E to the minus tau h is known. We don't know it, but suppose we knew it somehow. Then we're going to consider this P sub L and as a function of this unrolling. Okay, so set up the picture here. This horizontal axis goes to the left. It's a label of L. So L goes from 0, 1, 2, all the way to capital L. And by the way you hit, by the time you hit the full L, you've recovered the whole thing. Okay. We're going to start from 0, the first time slice. When we do this, we pretend that we know e to the minus tau h. So this is known, and then the trace is known. You evaluate it. It's one number. It's the partition function, and that's this z. We're going to start out. This first step, p0 is a constant. It's equal to z. Okay. Now we're going to create the first slice by sampling some fields. And we sample them according to this integrand because we're supposed to do an integral over only one set of variable x1. So we can sample these x1. And I've shown two paths here. So it's supposed to be somewhere here is 1. And I've shown you two paths. And you can imagine a lot more, right? These paths would now, in other words, P1, x1 would have different values. And this is the value. Right? They would have different values. And then I just go on to the next one. It's x1, x2. So now I have even more paths sampled. These are x1, x2 paths. And they have different values. And I keep going until by the time I've unrolled the whole thing, I've just sampled all the possible fields, and I get a distribution here. Right? That's in normal AFQMC, you would just be operating here. Right? You sample these fields, and you get a distribution. But let's consider when you start out, this is positive. The partition function is positive. And you can make tau arbitrarily small so that each time when you unroll one of these, the values are continuous. So then you start from a path that's positive. You, at some point, because it's stochastic, this value can become 0. And I'm going to consider that point when you exactly a path land on 0. This p is 0. You cannot go from below there, right? You always come from above. There's always a first time when you land on this position, you get a 0. When you do, what happens? Well, suppose it's here that you've landed at 0. That just means if you continue the rest of the thought experiment, what you're going to do is you're going to, suppose you have infinite computer power, you're going to integrate all of these e to the minus tau h. You just create these paths. When you've integrated all of them, what do you get? Well, you get 0, right, according to this definition, because this particular path segment is fixed. The rest, if you sum over all the possible fields, you get exactly 0 as predicted here. So that just says whenever this path hits 0, all its future descendants are kind of symmetric about up and down. You get, when you sum them up, you get exactly 0. So
The
in,
distribution of that point where you cross 0 is stochastic as well.
yes,
Okay. So you have a certain average and you have a certain width of that distribution.
Yes.
Any idea about those?
yes. So this is an abstraction of, in standard AFQMC, when you sample these paths, this is X, capital X, containing all the fields. So this is the last time slice. When you sample all the fields, what you get is, if you look at the determinant values, right, you have positive signs and negative signs. If you were able to do a histogram of the determinant values as a function of path, this is, of course, this one dimension is a many-dimensional space, right? It's the size of the lattice times the size of imaginary time. But in that space, if you did a histogram, it would look something like this. It would be basically 0. That's why when you do the integral, you get 0. But if you looked carefully, I claim you're going to see a red area, which is a symmetric image of the negative part, and then a little green leftover area. This is the signal you want, right? The rest are canceled. And that just corresponds to these, at some point when you hit 0, you turn into a red path. And the red paths are symmetric about this axis, so they're like this. And it's only,
It's a nodal surface.
there's a supernodal surface. So far, node has not made its name. There's a difference, that's why I didn't want to say node. But there's a 0 that's important. And in a second, I'll comment on why this is different from a node.
It's in a different space.
It's in a different space,
Oh,
right?
okay.
So basically, this is the contribution to the red. And what you want is, this says anytime in this path, in this procedure of breaking time invariance, right? At any time, if the path, if this p goes to 0, then all the future paths collectively will contribute 0 in z. And therefore, a complete path, when you finish from 0 to L, would only contribute if the entire path stays above 0. And of course, when you make this longer, right, when you make the temperature lower, you're moving this vertical axis further to the left. The path gets longer. The probability that the path at some point will hit 0 grows exponentially. That's why you have an exponential problem, right? So it always happens, and it's always, when it happens, it's exponential. The only exception would be if somehow by symmetry, like in the half-filled Hubbard case, this path goes to 0 but never crosses. Then you have no sign problem. That's the only case when you have no sign problem. Once we know that, we know a rigorous limit how we could in principle control the sign problem, which just says you have to control, you pick out only the green path.
Can I ask you, see, so here your reasoning would be, you follow the path, and at the point it crosses 0, you stop, and then you take another one, crosses 0, you stop, and you find you see all the paths eventually this way and sum them up.
Yes.
Is it something like this?
No, so you have an ensemble of paths.
Yeah.
Whenever a path touches 0, it's discarded. It's only the path that stays above, that never touches 0, that makes a contribution. Yes.
Positive all the way.
Yes. So you notice that if you do this with an actual ensemble of paths, you would get 0 efficiency because eventually everybody would die. But there is a balance when you do the constraint that would allow the green path to grow. And
Yeah, so what's your procedure to find that long path?
so here it is. We have the rigorous constraint is to, at every time slice, to impose that this is positive. The big problem, of course, is we don't know BT, right? The constraint eliminates all the noise paths, the dashed lines, and then in practice, we use a trial BT. So, and this reproduces how, with a trial BT, you can execute this for e to the minus tau h. For example, take the mean field, right? Take the Hartree flock. So if BT is a sum over mean field, that just means, by the way, with this auxiliary field language, it just means you choose some saddle point, right? You choose a point that you think is the best representation, and you fix the path, you fix the field value there. So then once you have BT as a sum over a mean field, this trace, again, could be evaluated. It's a determinant. So it just takes the form of, I'm sorry, I didn't write it out, a determinant of 1 plus all the BTs, which are now mean field propagators, and then BXs, right? So the sampling, we do it this way. This is that thought experiment again. We start out by, so these red dots are meant to be the mean field values. So you're sampling auxiliary fields. Suppose the auxiliary field value 0 corresponds to a mean field solution. Then you just set all of them to 0. So that's how you start. And then you, now you're going to try to generate the first set of fields.
That's a time-dependent mean field?
So you could make it time-dependent.
But what do?
We make it time-independent. The density matrix.
Stationary path, actually what's called stationary path.
Yeah, yeah.
Okay.
So
It's the zero frequency.
right, to generate the first field, you use P1 over P0, where P1 is just the, it's this, over P0, which is a constant, and you sample the field. But when you sample the field, you subject it to this being positive. And then when you are sampling the next time slice, so this is imaginary time, right? When you're sampling the next time slice, you sample P2 over P1, conditional on the 2 points, the path segment that you've already created. So P2 over P1. You sample that, and that imposes that P2 is positive. And so on until you've undone the mean field path. By the time you hit here, you've created a full path. And notice that these just cancel, right? So by the time you're done, you've sampled PL, the whole thing. And so you sample the determinant, the original determinant, but under the constraint that in the path, every point, it stayed positive, given this approximate thing. So this BT, the use of BT in imposing this constraint is approximate. But you're not, notice you're sampling the correct distribution under that constraint, right?
Can this be translated in an important sampling of the auxiliary fields?
Hmm?
Can this be translated in an important
Yes, this is just like important sampling.
of the auxiliary fields?
Yes, of the auxiliary fields. In fact, in practice, that's how we implement it. P1 over P0 could be translated into a, it's similar to a hybrid Monte Carlo, what people do, or it's a force bias. How we do it is a force bias.
So after you create a path, so let's assume you create a P1 over P0, and you create an ensemble of fields, which will propagate various time intervals, and you'll have an ensemble.
Mm-hmm.
You can simply take, randomly, from that ensemble, stick them together and do the rest of the path. Wouldn't that work too? Because basically, you want the path, to be basically a short time propagator to
Yes.
be positive.
Yes.
And basically, this is what you're enforcing all the time.
So this has I may have misunderstood you. The path is time dependent, and
Yes,
that's
it
sort
is.
of one of the problems. If you are here, it's good, and up here you impose the constraint. Up here you impose the constraint. If you go back and change one of the field, you could affect. This now could
No,
violate
it's
the
clear.
condition.
No, it's
Yeah.
absolutely clear, but anyway, why don't
So it's like the restricted path that you kind of have a reference, and this reference.
Is this a proof that in this way you get the correct answer?
Yes, well, the proof is on the
So-
previous page, right?
Because I didn't follow, everything, I'm trying to get the idea.
Yeah.
But you can think that this is a mathematical proof?
Yes, the previous page, that's the mathematical proof. So of course, in practice, we're not achieving the exact limit. But when you plug in that, it's mathematically correct. Bob?
So are there some cases where this could be proved to be preserve an upper bound property?
It doesn't preserve an upper bound property, unfortunately.
It doesn't in the nuclear case, but I was wondering if simpler cases maybe it would.
But it is second order.
It's accurate, but it could be up or down. It's not an upper bound.
The word dot products of giants pronounced
Time translation invariance is broken.
Yes, yes.
When I say second order, I mean that,
Second order in some error.
yeah,
Yeah.
that if your the error is proportional to the square of the error.
But this is an imaginary time, and so it's not the proof.
That right?
So
So I'm hesitating because I don't quite know how to define the error. How to define the, I guess if you write bt minus exact bx,
Yes,
and yeah, ask is that second order?
yeah.
I don't know.
What about the free energy, for example?
Yeah, I don't know if it's second order. I think it probably is. I don't know. So let
So
me,
your statement is that you don't know of cases when this procedure won't work. It will give you an incorrect result. Is that correct?
so
That's the-
it's biased, right? It's going to, I'm going to show you results. It's not exact.
No, but you see, you'll have an error, and that depends you see on the size of the ensemble,
Mhm.
right?
No, the error doesn't depend on the error only depends on one thing, what you put down as BT.
What?
BT, this trial density trial propagator that
Yeah,
you
but
put
this
down.
is the ensemble, you see,
Yeah.
in my language.
That there's no, so you specify a BT, and the BT in the ground state case particularly, you could dial over a class of BTs and we could see improvements and so on. But that's the only thing it depends on. And as for whether it works or not, well, it's approximate, and for things up to what you would definitely call strongly correlated system in condensed matter, where the exchange correlation energy, the correlation energy would be 10, 20%, 30% of the total energy. It works well.
This, you see, somewhat, you see, I show something, you see, which is not quite the same, but somewhat similar. People take the path, make a Fourier transfer of that, and then they take various Fourier components up to a certain cutoff. You see, and in principle, you see, in that way you can control, because if you take only the zero frequency,
Yeah,
you have a stationary path, you don't have a sine problem.
yeah,
You see, you take the next component, you see, which is one oscillation only.
yeah.
You see, depending on how many you sample, you see, probably the sine problem
Yeah,
is minus.
so-
So is this equivalent to that? You can translate
No,
it to
it's
that?
not equivalent to that in that, well, I guess there's pluses and minuses. From a framework point of view of thinking about it, this is less systematic than that. That, in chemistry, for example, people are doing perturbation theory. They want to be able to identify which order you're doing. Well, this is kind of a, it just says we're going to have this global constraint on the sign or phase of the determinant. So that's kind of a drawback if you want. The advantage is that it is often much more effective, because the kind of perturbative or order by order thing, they often don't converge very well, right? They have funny behaviors. And when you take out, I mean, in practice, you don't go very high orders. So
Well,
typically the errors would be
in
much
the
bigger.
asymptotic series, you see, introduce a convergence factor, then you're all fine.
And
We do this in physics all the time. You see, when you define propagator, put the 1 over minus I epsilon, that's exactly convergence factor.
Yeah.
To deal with this problem.
so put it this way, the kind of hierarchical approach, for example, in a case like the Hubbard model, would be far less effective, I think, than this.
So since you don't have the variational upper bound property, how do you choose between how do you decide between the quality of two different trial functions?
So we don't have, unfortunately, in this framework, the trial density matrix or trial wave function is a Slater determinant, or a linear combination of Slater determinants. So we actually, from a practical point of view, don't have that problem because we're quite limited in what we could use.
But suppose you use a Slater and a BCS, then how do you choose if the system is paired or not?
So there are some internal,
You don't have a problem with the grand canonical ensemble because you sum over the entire single particle spectrum. So you don't limit yourself, you see, the trial wave function, you see, you'll have a trace. So I think, you see, for grand canonical simulation, you don't have the problem with the trial function. If you do a canonical simulation, yes, you'll have that. But grand canonical, you won't. And he talks about grand canonical. Am I right or not?
so I'm now going to go to, in fact, ground state, a canonical fixed number of particles
That would be-
calculations. And I should wrap up pretty quickly, I guess. Okay, so let me do that. So now going back to ground state, what happens with the sign problem is just due to, so these are the two orbitals, remember, for the same color fermions. these orbitals are going to be in this propagation. The coefficients are going to evolve under these external one-body operators that are functions of fields. When they do that, the fields are stochastic, they're going to change, and it's possible that one would twist over the other. They would have a super exchange. One would become the other. And that's when you get a sign. Right? So, and in fact, in the general case, when you have a Coulomb repulsion, you get complex operators, and then these evolve in phase. And you have a whole occupancy of the complex plane of different equivalent phases. So to eliminate the sign problem, right, we've done the harder case, the finite temperature. In the ground state, you just take a trial wave function and you say if this determinant has a zero overlap, it starts out positive. And if it reaches a zero overlap, then a super exchange has happened and you stop the path. And notice that the connection between this finite temperature and ground state, right? The finite temperature, we have these BTs. Now, BT over anything, A stands for anything, anything that's not orthogonal to the ground state Hartree-Fock solution or something. This operation just leads to the corresponding ground state of that mean field, right? So it's the same, you're just taking a mean field solution. Now, when you have a phase problem, I won't go into this. You have to basically now, instead of a plus-minus symmetry, you have in the complex plane of real axis, imaginary axis, you have a circular rotational invariance. So you have to break this with a gauge transformation. I won't go into the details. I'm happy to talk more, discuss more about it. Same idea, though. So now going back to this Hubbard example, this is the phase, this is the sign fluctuation. And now when you put on this constraint, that's the blue line. It certainly doesn't have the fluctuation anymore. And of course, you could go on forever. This is just a stable, if you wish, boson calculation. Right? It has n-cubed scaling in this case. And it's approximate, but very accurate. How do I know it's very accurate? Well, in this case, I do know because there's an exact answer. And that's the red line I've just called up. And if you blow this up, this is the red line. And this answers the question. That's the blue line. So it's not variational. It came below the exact answer. How big is it? Well, this is when you are a practitioner, you follow some standard recipe. It'll tell you that for this system, the conservative Trotter step tau to choose is 0.05. When you do that, you can be safe that the Trotter error is gone.
In terms of T, right?
Yeah, in terms of T. So, well, this is half the size of the Trotter error. It's the.
Wait, maybe a sense of how large is the dependence of this discrepancy on the choice of the.
Yeah, so I have some examples later. Hope we get to. So it's a pretty small error. So let me give you just some sense of applications. We do this for molecules, which now, instead of having the Hubbard interaction, it has a two-body matrix, Vijkl, that depends on the matrix elements, and one body. But you could do that and do this phase constraint. What we do is we set up the Hamiltonian, and we use a density functional theory wave function, or a Hartree-Fock single Slater determinant trial wave function, to carry out this BT, or in this case, psi t, the constraint. And this is, you could view this as an automated post-Hartree-Fock or post-DFT, because you carry out the mean field DFT or Hartree-Fock calculation. You feed this into the QMC, and then it goes. In molecules, the accuracy is comparable to the couple cluster CCSD with perturbative triples, which has been functioning as sort of the gold standard in chemistry. It's an expensive method into the 7th power scaling, but that's the best one could do for small systems. Yeah, it's a mixture of particle number and basis number adding up to the 7th power. So it's not exactly.
But your n is particle number.
Yes, I'm being sloppy here. This is also a combination of basis and particle, but adding up to 3rd power. So we have solid calculation in solids up to 54 atoms or so using full plane waves. So this would not have a basis error effectively. The basis error would be much smaller than, many orders of magnitude smaller than the statistical error when you do a plane wave or grid. But the chemistry calculations would have basis errors. So here's a little example of F2, the molecule F2, fluorine 2. And what's happening is so there are 2 atoms. You pull the bond apart, and you ask, what is the energy as a function of this bond separation? And the bond separation is represented by R over RE. E is the equilibrium, the actual molecule bond length. So 1 is at equilibrium, and it's a minimum. And then when you pull this apart, it's basically going to eventually be the van der Waals. So it goes to some atomic, 2 times the atom energy. So this is a part. And this is a small basis where people have done this R, CCSD, not just T, but up to Q. This is basically exact now. And you can see that, so I've showed you 2 couple cluster answers. This is the gold standard, now breaking apart, right, when you pull the bond length. It's very good at equilibrium, both of them, but it breaks apart.
What's the R for?
Restricted. It just starts from a restricted Hartree Fock or unrestricted. And this is what, oh, sorry, I forgot to say, this is the QMC answer, the blue line. It matches the exact answer very well. And now we go to a big basis. And this is the equation of state. Now, 1 is here. Sorry, this part is cut off, right? So this is the full equation of state. The blue line now is the QMC, and that should be the standard now. Our answer, that should be the standard. And the typically used local density approximation, for example, this is LDA, which is off estimating the binding energy by a factor of 2. Got the bond length basically right. And a popular chemistry functional is B3LYP, it's just a mixture of stuff. And it gets the binding energy right, but the well shape here is off. It's too tight. And that's going to cause a higher harmonic frequency, right? In solids, that would correspond to a bulk modulus. And so on. And this is another one. And when you calculate large basis set, you can see that this is the QMC compared to experiment. And that's the equilibrium bond length. This is frequency, and that's dissociation energy. So you get the curve defined. And you can see that these quantities are reflective of that curve, basically. So I think I'm just going to skip over this. But this is, I'm not going to give you the details. This is a little application. That's graphene, which has generated a lot of interest. And the idea with graphene is that it can be, maybe it could be used as devices because of many tremendous properties. The only problem for devices, spintronics devices, is that its pristine graphene is non-magnetic. It doesn't have a magnetic moment. So the one idea here is to take a magnetic transition metal atom cobalt and to move it toward the graphene sheet to try to induce a local magnetic moment. So this is a toy calculation. Basically, people then are trying to say, well, does it, where does it sit as an equilibrium position, and what kind of a magnetic state there is? Well, these are my 2 popular theories, GGA and then B3 lip again. You can see that they predict very different things. The green curve, there are 2 sets from GGA and B3 lip. They tell you, GGA tells you that, so there are 2 spin. This spin refers to the cobalt magnetic moment. So when you, equilibrium position, this is height, has 2 different natures according to the 2 different theories. The GGA says that the low spin state is a minimum, and the B3 lip says the high spin state is a minimum. And the minimum positions are off too. So we can carry out QMC calculation on this. It turns out that's the QMC answer. There's a couple features. You can see that neither one really got this interior part correct. And there's a trivial modification too. There's a third curve, which is the van der Waals limit. So when the H is large, there's a van der Waals limit. And it's well known that density functional theory has trouble dealing with van der Waals systems. And these are
Which is which again?
So the blue curve is quantum Monte Carlo. So that's low spin. This is
Okay. No,
so as you push cobalt toward graphene, it undergoes 3 things. It's the naked atom, that's this curve. There's a shallow well here, it binds. And then that's 3/2 spin. And then it changes to another 3/2 spin that has a, from a SD transfer. And then it goes to a spin 1/2 by transferring some electron into graphene. So that's the kind of the physics of this.
How did you choose BT in this case?
So these are all, we try these different things, and we show that they don't depend on them. And in fact, in this case, we have a very good internal check, which I'll come to in a second. But I'll skip the details now. Basically, so this, so we can resolve this problem. We can say, make a prediction. Experimentally, they're trying to use STM to measure this, but
This-
the barrier is too small, so they get a mix. They seem to get a mixture.
This is only valence electrons calculation.
This is using a small cobalt core replaced by pseudopotential. It has about, I don't know, some tens, not quite 100 electrons.
No, but so what you have actually, you have the 3D and 4s electrons.
Yeah, that's just referring to the outer, that's the nature of the spin state.
Mhm.
Of course, the actual calculation has the interior electrons interacting as well. This is just referring to the nominal spin state, how you characterize it. Okay, so I really should stop. I'm going to just tell you one thing, I guess, about release and then stop. So this is in terms of what we've done recently. So this brings back release. Let me just go there. So this is this Hubbard example again. And you can release the constraint, right? When you sample the path, you don't let them cross zero. Well, you could, after they converge, this is in the ground state, you could lift the node and choose to let them go for a while. And this has been done in DMC. It was done many years ago by David. And you could do the equivalent of that in here. And the thinking is that because this, with the super exchange effect, right, the sign problem due to bosonic or one-body ground state is completely removed. So the sign tendency is much weaker, so you could release it longer. That's the hope. So you can release this, for example, that's what happens. It goes back to the exact answer, and now it picks up in fluctuations. And this is showing, addressing an earlier question about sensitivity to the wave function. So this is the spin structure factor. And remember that when you dope it a little bit, it has a strong antiferromagnetic order. So the structure factor of the spin-spin correlation has a peak at pi. And you can see it here. And the exact answer is supposed to be this black curve. And now when you do the constraint, you can see that it gets the structure right, but it makes an error. And when you release it, it basically recovers it. So here's on two different wave functions. So this is the double occupancy, which came up earlier, as a function of u. We're now scanning different u's. So the double occupancy, what I'm plotting here is the average interaction energy. So that's u times double occupancy. So as you increase u, double occupancy is coming down exponentially. But u times double occupancy gives it a linear curve. So this is going to go up first and then come down exponentially, right? That's the shape of the curve. The free electron wave function would just predict that it goes up because the free electron doesn't know about correlation. It gives you a constant density. So n up times n down is a constant according to the Hartree-Fock solution. So you get a line that goes like that. Now we use this free electron to do this trial wave function, Vt, to do the calculation, and that's the answer. Now we do a different one. We do Hartree-Fock, unrestricted Hartree-Fock, which carries the free thing, and then Hartree-Fock just gets up and down to avoid each other. It resorts to breaking spatial symmetry, so this comes down like that. We use that trial wave function, we get this purple line. They basically are indistinguishable. And then when you release them, you get the exact answer. Okay, so with this release, we could do Hubbard model on the 12 by 12, 100 sites or so. Add the interesting fitting. This is a ground state energy. We think this is basically the exact answer. Now this is one example, I forgot what system, of a release, right? Same thing as the 4x4, you could do this. In fact, this is probably the 4x4, you know the exact answer. And we do one more thing to know, sort of, to try to monitor whether it's converged. We calculate the variance of the energy. And the variance, when it's converged, needs to go to 0. So this is the variance as a function of convergence time. And this is plotting the energy versus variance. And if you extrapolate, it kind of gets pretty close. So going back to the Hubbard model, I asked this question, what happens when you dope it to the magnetism? Here's the answer, we think. That when you calculate, remember these lines would just correspond to antiferromagnetism. So when you calculate, we calculate these rectangular lattices. 8 by 128 is the biggest lattice we dealt with. So that has 1,000 sites and about 1,000 electrons, a little less than, because it's 0.9 electron density. So you calculate the density, you see a plot like this. Basically, it's AFM. But notice that there is a mismatch. There's a dislocation there. And when you do a 8 by 64, that's this. there are 4 dislocations. And when you plot these, so these are staggered magnetization. Basically, it just says if you have antiferromagnetism, I'm going scanning along this line. If you have perfect antiferromagnetism, you'd have a horizontal line. 2 of them, because every other one is also changing sign. So 2 lines, 1 positive, 1 negative. But you can see that these have a big envelope on top. That's because it picks up, it's antiferromagnetism with an envelope with a modulation. So that's the answer. You think that the system, and these are free electron wave functions, so there's no such structure, right? The calculation emerges.
Did you try to do the square, 32 by 32, for example?
Yes, we have 32 by
You
32.
have the
Same thing,
period?
yeah.
You mean you'll have the same?
Yeah, a few years ago, we could only do about, just barely do square. We could do not quite 32 by 32. As a result, we would see a broken symmetry thing that's a blob. And when we do scan this, we could determine the wavelength. And then you go back to 32 by 32 with the right wavelength, the thing comes out. So a comment that this is the repulsive Hubbard model. We've answered that it's a modulated spin density wave. It has a long wavelength. The wavelength is 1 over doping. So it vanishes. The wavelength goes to infinity, right, at 0 doping. And that's how you get back to a perfect antiferromagnetism, right? The envelope gets bigger. Eventually, the wavelength is infinity. You get back to a perfect thing. And this, there are people interested in optical lattices with negative U interaction. So because of a particle-hole symmetry mapping, it turns out the repulsive Hubbard model maps into the attractive Hubbard model with a spin particle-hole transformation. So the implication for this result would be that if you did optical lattice with negative U, but spin imbalanced, 1 majority spin and 1 minority spin, you would see one of these exact FFLO state. But in particular, it's a LO state with the excess spins are fluids living at the node, and the pairs would form BCS pairs with a finite momentum. And the momentum is proportional to this wavelength that we talked about. Okay, going to stop now. This, I mentioned that we know we have the right answer. This is the cobalt and graphene thing again. Because we could do a small basis set and just do this release. And when we do that, we see that the phaseless makes an error. This is in terms of the well depth in EV, so of negative 0.03 EV and 0.06 EV. We benchmark these couple cluster things, and these are the errors they make. Of course, the DFT errors would be enormous. So I'm going to skip all of these and go to sorry. So I told you about constrained path to control the sign of phase problem in the auxiliary field framework. It tends to have less error than fixed node with the same trial wave function. In electronic structure, the accuracy is roughly at this level of couple cluster CCSDT at equilibrium. It's better for multi-reference or stronger correlations. For model calculations, this can predict new phases independent. It's insensitive to a large degree to the trial wave function. And I told you about just releasing the constraint. But some of the other things we're doing excited states. I'd be happy to talk to you about any of these. Treating periodic solids with downfolded Hamiltonian. This is basically a consequence of having a basis where you could throw away basis functions that you think are not less relevant to the physics and treat a simplified model. And the use of better trial wave functions. We've also used BCS with Kevin and Joe and Stefano. There's some recent effort in terms of using Hartree-Fock but restoring symmetry. You obtain the Hartree-Fock solution, but after you project back the symmetry, and that seems to be very promising. I can talk to you about it. Thank you.
Question. In the calculations for the repulsive Hubbard model, do you have a way to determine where the transition from metal to molten insulator is?
The metal to insulator. You mean at half fitting or?
Yeah.
So half fitting, it's insulator all the way.
Even for extremely small U?
Yes. But that's a problem with that phase diagram. Now, when you dope it, we don't know what the phases are. There's this spin density wave phase emerges at up to So we scanned some U's. The results I showed you are at U of 4. That's an interesting U, and 8 would be half bandwidth. 8 would be bandwidth, and that would be where between 4 and 8 is where you want to be.
I think that other theories predicted a finite critical value of U. I mean, if we set U equal to 0, it should be a fluid.
Yes.
matter.
Yes.
You say
So
that
it's
any
critical. The
finite-
claim is that it's critical. It's not our work, right? This doesn't have a sign problem. So according to QMC, when you turn on U, let's see if I could find.
Like Assad, for example.
Yeah, Scalapino and others and Scalata have done this at finite temperature, and basically, you start from very small U, and then you do finite size scaling. It seems like the critical U is at 0. But of course, that phase diagram suggests there's a large metal insulator transition rate within DMFT. And that was my point, that I think it's not really converged yet, as the textbook was trying to indicate.
One question. Well, I got slightly confused with the explanation. So in the imaginary time, you show that there is very nice convergence to some value for positive restricted path. And then if you do the release, then this value changes a little bit.
Mm-hmm.
Like that. But then I think at the beginning you said that even with this positive path, the result should be exact in the sense that,
So the result will be exact if you have the exact BT to constrain it. If you don't have the exact, you make an error. So when you release it, it tries to.
And then if you do the release, then do you know how it will go to the exit result? Should in an exponential way?
No. We don't. So it depends on how good your initial point is, and it also depends on the trial wave function you use for the energy, for example, because we measure this with the mixed estimator. So the energy is dependent on where you start, and so it's important that you start from this converged constraint path solution. And then if you have a bad answer, we've seen cases where it would be non-monotonic. And so that's why this variance thing is useful. But there's no guarantee that it would converge there exponentially, I don't think.
Similar question. When you approach time translation, invariance is broken. And when you talk about energies, you talk about, you mean, I guess, the eigenvalues of the transfer matrix at the most converged slice.
Right. So it's important. So let me distinguish then the finite temperature version and the ground state version. So all these applications are ground state things. So there it's an open-ended path, and you have to converge, and then the measurement is done there. And so it doesn't the fact that you've broken time translational invariance is irrelevant in these calculations. Now in the finite temperature calculation, we create the whole path, and then we can, now we have the whole path. We go back, we either measure the observable at the end or in the middle, and there are going to be fluctuations. There are going to be, fluctuations and differences. So most of the quantities we actually average over the path.
You mean over where you put the operator?
Right, over where you put you have a whole path of fields where you insert the observable. In the unbroken version, the original version, it shouldn't matter where you insert it. It's a loop. But now, since this way of thinking about it, we break a beginning point, right? We break the loop. So it matters where you insert it. And it seems like that's a higher order effect. You don't notice, we didn't notice any patterns to it.
Does the exact BT break the time?
The exact BT wouldn't, I think it would restore the symmetry. One comment I wanted to make, right? I guess in response to Mel's comment also. If you think about the non-interacting problem, right? There, if you use the non-interacting BT, that's exact. So that comes to an exact calculation, even for imaginary time correlation function. So that's different from the fixed node answer, right?
Which
That's why I was trying to distinguish the node.
means you shouldn't regard it as a,
It's not a node, real space node. It's
well,
a,
I know
yeah.
it's not a real space node, but there is it's a node in some space.
yeah, yeah.
Okay, so we will have, thank you, Shiwei, again.
Thank you.
We will have no time for
It's okay,
discussion.
Shiwei, take it on.